Company Limited and ISLE heartily welcome one and all present here. Our solo act is never successful in this pandemic era. The theme of this webinar is designed to create complete component ecosystem. Semiconductors have been a key enabler in the advancement of electronics and continue to play even greater role with introduction of smart technologies. This ensemble will give us a bird's overview and enable an environment which will adopt eco-friendly technologies complementing to each other. We can see how lighting can coexist with air conditioning applications. This is a revolution of coexist and complement to each other. Seoul Viosis is a pioneer in bringing new technology to reach many people. With the collaboration of ISLE and Ishrae as a community of technology has come forward with a common platform. We have today three distinguished speakers who will enlighten us on the latest trend in UV and air conditioning application. I was really looking forward for this day. I thank you very much for this honor. Over to Mr. Prakash Bhartija. Mr. Prakash?
Sorry, you need to unmute, sir.
Please unmute.
Yes. Hello. Hello.
Go ahead, Mr. Prakash.
Hello. Good afternoon, everybody. Can you give me a share screen?
It's enabled, sir. You can share the screen.
Okay. Is it visible now?
It's visible, sir.
Okay. Good afternoon, everybody. On behalf of ISLE, I welcome all the participants and speakers for this program. It is our pleasure to welcome on behalf of ISLE, which is a national body which has completed 37 years, and which is a professional body of the scientists, engineers, architects, academicians, researchers, designers, students, and all others interested in the field of lighting. Our main aims and objectives are the promoting the art, science, and practice of lighting technology, advancing education and research in lighting technology, formulating lighting codes, guides, and technical reports, maintaining liaison and technical interaction with the national and international organizations, and cooperation with the Bureau of Indian Standards. Our vision is a very important activity which is there, as I think most of you may be aware. There are national codes are there in the different fields, like National Building Code, National Electric Code. Similarly, there is a National Lighting Code, which is published by the Bureau of Indian Standards. And ISLE has got a very important role in formulating the same. Initially it was formulated about 10 years back, and now it is under revision, and that work has been already in hand with the ISLE. Another activity is the National Lighting Center of Excellence establishment, which is in the progress. Then another activity is the certification for lighting designers like NCQLP in USA. Another activities like educational skill development, awareness programs for students and energy savings, and postgraduate programs in lighting, technology, and energy. Our ICLE works through 7 state centers, all the 4 metros. In addition, Karnataka, Rajasthan, and Madhya Pradesh. So these are 7 state centers. Then there is a provision of local centers which are there at Bhubaneswar, Pune, Hyderabad, and Guwahati. And we also got student chapters at the different states. Today there are 17 student chapters in the country. We are closely associated with the Bureau of Indian Standards, Ministry of Power and Renewable Energy, Bureau of Indian Standards. Also internationally, we are working together with the IES Illumination Engineering Society of North America, Lux Pacifica, Institution of Lighting Engineers, IES, and the SAARC countries. Our present body, governing body member of ICLE for 2015 and 21 is being led by Mr. Dilip Kumar, who is the CEO of K-Light Group of Industries. As far as Karnataka Center, this program is being conducted by Karnataka State Center, and the chairman is Mr. R.C. Krishnachari, along with Mr. K. Kailaslevan, Honorary General Secretary, and Dr. Vidya H.R., Honorary Treasurer. Other members include Mr. Satyendra, Mr. M.S.N. Swami, Mr. Bhavani Prasad, and Ajay Gupta. This committee has taken over recently, and they are doing very good work activity. The first activity they have done with the MOU with the colleagues with the national centers. Then, as I mentioned you, that we are working closely with the National Lighting Code, and this is being done under the leadership of Dr. Rajat Mandal, with the Honorary General Secretary of ICLE. Accepting the challenge of COVID, about a year back, we started a certificate course in basics of lighting and illumination, 6-month e-course, which was addressed by 63 distinguished lecture experts, not only from India, but from all over the country, and which was attended by 76 participants from all over the India and also South Africa and Saudi Arabia and Africa. Another important activity which we have done is the position statement on the germicidal ultraviolet irradiation, which is being submitted to the BIS for the formulation of safety and performance standards. Appreciating our work in the spreading the lighting education, SOCHM, which is a national 100 years old body, they have joined hands with the GEM Council of the ICLE in July 2020, and since that time we have conducted so far 12 technical programs on the different fields in the field of lighting by the different experts from India and the overseas. We also publish every 2 months our e-magazine, that is Light India International. Our major activity is in the field of lighting education. So you can see, starting from 1993 till now, we are actively involved in the spreading the education in the country. Our main focus is on the student chapters in the different engineering colleges and architectural colleges. So far we have got 17 student chapters throughout the country. The benefits of them, that we want to give exposure in the subject of lighting, activities, help in projects, placement, discount in events, organized, e-copy of ICLE newsletter. Our fee is very nominal, and you can see here, we have got a provision of the institutional member, fellow member, and associate member. Although the name of the organization is Indian Society of Lighting Engineers, but actually its membership is open for anybody who is interested in the subject of lighting, irrespective of its qualification. Even if it is illiterate, he can also join in the one or the other category of the ICLE. With this, I welcome to the world of lighting. Get enlightened. Thank you. Hello.
Thank you, Mr. Prakash.
Girish, you'll play the video now?
Yes, sir.
Law.
Can I start?
Yes.
Ashi?
No, no, wait. They are going to play a video. Girish, are we going to play Ishrae video?
Sir, you can share your presentation, sir.
Jayhawk,
Yes.
you can start your presentation.
Thank you, Ashi. Ladies and gentlemen, thank you for inviting me this presentation and with the seminar. And I'm very pleasure to introduce our technology, like the BioLase technology. And now I can start. Today, I would like to introduce the future with biology technology in air and refrigerator. So okay. Okay, the presenter, I introduce myself. My name is Jae-hak Jung, and I'm working for Seoul Biosys since 2014. And I'm in charge of the UV business division located in Ansan, near the Seoul, Korea. And I'm VP level, and my education is a PhD candidate is a major. My major is the environmental science, and master degree in Sejong University in Korea. And I received some award about the minister's award about the climate change. It's a paper, and then I'm working experience is 14 years experience in semiconductor industry. This is the clean room device, and then developed for the photocatalytic filter system using UV LED. And one more thing is developed for the volatile organic compound condensation system in the clean room, like the semiconductor fabrication site in Samsung and LG factory. Okay. As you know, the COVID has changed the world. So one of the major home appliance company called Samsung to launch the more appliance with the UV LED technology in 2021. So the Samsung is expected to apply the UV in around 20 to 30% of their home appliance model. And we already applied our UVC LED to Samsung for the air purifier system, and they will expected to apply our UVC LED in their home appliance model. I believe the India market is very big huge, and then India home appliance factory will adopt our UV LED. I hope. So the UV market trend is the UV LED market will increase from 296 million in 2019 to 1 billion by 2022. As you know, due to the pandemic situation, the purification application market will expand to 2.8 billion by 2025. So the main application is surface disinfection and air disinfection and water disinfection. So we are focusing the three kinds of the disinfection purification application. And we compared the 2020 and 2025 UV LED device market size. So the air disinfection and surface disinfection, even the water disinfection will grow hugely. So we are focusing the three kinds of the application. So so what is the ultraviolet, like the UV? UV is the functional light. So the sunlight delivered UVA and UVB in land, and the UVC is the cut the ozone layer. So due to this reason, UVC light cannot reach our land, or even we cannot use this UVC LED. And currently, some UVC lamp, more people using the UVC lamp, and we developed a UVC LED, and this technology is using the many small device, adapted device, small device, and then we can adapted hold everywhere in the into your life. So the UVA and UVB, UVC is the different wavelengths. The UVA is the 320 to 400 nanometer range, and then UVB is the 280 to 3020, and then UVC is the 200 to 208. And we use the UVC light using the sterilization function, and then for the UVA case, we use the deodorization, like the air purification with photocatalytic filter, and some people using the UVA light the adapted insect trap, and some curing application, they will adapted UVA LED. And for the UVB case, the medical device developer, they used our some UVB LED into their skin, resolve the skin disease or the some generated vitamin D. Yes. Okay. So and our company are leading the pipe application, and we can give some solution provider for the lighting, automotive, and IT application like this display and mobile and IR. And then last one is our business model is UV, and we are developing the UV system or solution to provide you. So the biology, so for the biology technology, I will explain. So the biology solution is the for home appliance. So all the home appliance, air purifier, refrigerator, air conditioner, even the dishwasher, some kind of the using water application, we can disinfect the air and water and surface disinfect, reach the 99.99%. So why customer using the UV LED? As a UV LED is the compared to conventional UV lamp. It's the UV LED is very small. It's the first good position, and it's a very good advantage is the warm up time. As UV is only the you can input the some the voltage or some current value, and then UVC evidence UVC can write immediately, and then conventional UV lamp is the turn on time, need to turn on time. So due to this reason, the disinfection time is the delayed. And the second one is the heat generation. UV LED is the low heat generation than compared than the conventional UV lamp. And then the UV LED is the eco-friendly technology, so no mercury, no ozone, and the energy consumption is the lower than the conventional UV lamp. So the our concern is the only the low power and the high price than the conventional UV lamp, and then we can develop the high performance and low cost version of UV LED. We are focusing. So what is the biology technology? It's the biology technology describes the know-how in developed manufacturing, testing, and validation of the UV products. And we using the different type of the wavelengths, and we can provide some distance, angle, and power and time. We combine these 5 kinds of the factor, and then we can give the solution to our customer, and the customer added their products some the added value, and then the customer make some money, a lot of money. Yeah. So what's the different disinfection method? When UVC irradiated some the surface, the E. coli damaged the pathogen and breaking the DNA. So next one is the easy. So the UV disinfection is the DNA structure destroyed when UVC irradiated. And then second one is the 405 nanometer UVA using the disinfection method. The inside the bacteria like the E. coli, they have some how to say how to say I forgot the propylene. They have some the propylene compound, and then the propylene compound adapted absorption the 405 nanometer wavelength, right? And then they make the reactive oxygen species like OH radical and superanion oxide, and then oxidation of DNA leaves amino acid degenerated, and then finally the bacteria less than bacteria growth or division. I mean the bacteria inactivation effect. So this is the UV disinfection technology, and then the UV LED is a very small device, so you can adapt it easily everywhere, and then you can control the when people go in or go out, and you can easily control it. Okay. So the it's a different type of the no UV treatment and UV treatment. So the left side is the exponential growth. The bacteria growth normally we don't use the UV. The bacteria will grow in surface or in the water or everywhere. And then when we treat the UV, the bacteria or virus cannot grow due to the DNA structure is break, like destroyed. So when you use the UVC right, the bacteria cannot grow. Okay. So we can so the bacteria disinfect need to the UV energy like the dose value as the square centimeter per millijoule, and then we can calculate and then normally the right source to surface distance is different, and then bacteria inactivation effect is the lower than lower. So we can calculate it and we can guide to you using our UV LED into your system, and then we can calculate the disinfection time or some the dose energy. So we have some simulation lab and then testing lab, so we can give you the solution or some guide to using our LED. So we already tested the SARS-CoV-2 virus, and condition is 2 centimeter and lysos-2 virus suspension, and within 1 second we can sterilize the 99% lymph efficiency with SARS-CoV-2. And you can see this graph, the various type of the bacteria in the virus, the absorption wavelength is different. Some E. coli is the main, is the 270, and the rotavirus is 270, and then MRSA, superbacteria is almost 70, and then E. coli is almost 265. Yeah, so very different wavelengths can destroy or disinfect the bacteria, even the virus. So we have a lot of some data, and we can guide you the disinfection or which wavelengths you can use, and we can what time is the disinfection time, and we can guide to you. So this is the test result for the SARS-CoV-2 in Korea testing lab, and this condition is almost same, and we tested SARS-CoV disinfection using our 100 milliwatt UVC package. After exposing the SARS-CoV-2 to the violet LED module for the 1, 3, 4 seconds, respectively, the research team observed the inactivation rate of the virus particle at 99.4% in 1 second, just 1 second. So this is the test report. You can see the 99.8. So as I mentioned you, we have the test lab in our factory, and then we already tested some the E. coli and Staphylococcus aureus using our LED and various distance to lysos to surface, and then it's a very low power and using the high power, and the different time. The x-axis is the time, and y-axis is the log inactivation. Log inactivation means the 1 log is 90% removal efficiency, and 2 log is 99%. The 3 log is 99.9% removal efficiency. So you can see the our test result. Yes, we can guide you the this kind of the test result. It's a E. coli, and then this is a Staphylococcus aureus. So our internal lab can use the two kind of the bacteria, and if you needed another kind of the virus or some the different type of bacteria, we can connect to our third party lab, or even in India, RC can help us to testing. So this is our very good solution, provide the solution to you. And the second one is the last one is the using the UVC only, and this page show the photocatalytic filter and this photocatalytic filter and UVA LED. And this is the titanium dioxide, and when we irradiate UV LED, titanium dioxide generated some the reactive oxygen species, and then the reactive oxygen species can remove the harmful gas like the VOC and pollutant bacteria, even the virus, and then they can reduce some of the harmful compound. And then our technology using the under 388 nanometer, and then we using the UVA 365 nanometer. 365 nanometer observed the titanium dioxide like 0.7%, 70%. So we can use the 365 nanometer. And this one is the we didn't generate the ozone report using the photocatalytic filter plus UVA and UVC LED. So we this is the Korea standard, and less than 0.005 micromole per mole, and then we didn't detect the ozone. It's a base like a background concentration. So the test summary and safe solution of viruses is we can kill the airborne virus and surface disinfection, and then safe virus technology. Okay. So the almost some home appliance company using the ionizer technology, and the ionizer technology generated some ozone. So our technology is no ozone, and then lifetime is long. than the ionized technology. And then IO technology can disinfect the bacteriophage and our using our LED. It's a very small time, like the 30 minutes, than ionized technology. Ionized technology is 16 hours and 60 cubic meter. Yes, and then it's almost we can use the every home appliance technology, and then biology solution for the air, water, and surface we concentrate, and then we use the already adapted air conditioner and refrigerator, and then the US HVAC company, they used our technology. This is a detail. It's one of China company. They're using our LED, and we tested in China lab. This is the US company. They used our module using their product. This is the air conditioner. We installed our UVC LED in their system, and then we tested the disinfection. We tested the virus in the 6 cubic meter disinfection only 30 minutes. Yeah, and then we have the solution to disinfect the water dispenser and water tank, even the dishwasher and tumbler. And then the water purifier can use the water tank, filter, water pipe, and nozzle. Yeah, this is the final presentation. Thank you for the how to say it. Thank you for the listening the presentation, my presentation. Thank you.
Thank you. The next speaker is Mr. Wanchal. He's currently working as a Vice President, Product Management for UV curing and water sterilization. He is a physics graduate from Hanyu University in 2002. He has done his Masters of Law, and in the field of law, he has a study of specialized area of law, product and patent, and gained international recognition, product patent and product developments. Since 2002, he is working for Seoul Biosis and Seoul Semiconductor at a global product management level. He is having more than 19 years of experience in the product development, especially world-class LED development technology and patent. He has worked and developed product for wide spectrum from lower UVC to visible spectrum, from 200 nanometer to 1000 nanometer, semiconductor chip technology, white LED package, patented sapphire substrate, the gallium vertical LED. Thank you, and over to Mr. Wanchal.
Thank you very much for your introduction, Arash. This is Wanchal Seo in Seoul Biosis. And it's my pleasure to have a time to introduce the BioLens, the UVC technology to you. Okay, I will start my presentation. So I think that you already hear much about the BioLens technology using the UV LED from the Jack's presentation. And my focus is on the LED itself. What is the LED, and then what is the different from the other blue or white LEDs? So in previous presentation, you hear about what is the UVA and UVB and UVC, and then what is the difference between the UV LED and the white LED? Actually, I think that you know very well about the LED itself because currently the commercial lighting, we are using the LEDs for the general lighting. So, and then but the UV LED is also the LED. It means that the lighting emitting diode. However, the light from this LED we cannot see because the range of the wavelengths is the ultraviolet. It's below the violet wavelengths. And then the difficulty of the making this LED is because of the component of the material is different from the blue or red and green. So in the left side over here, you could see the lattice constant and then the band gap. So how can the LED make the light from the semiconductor? So LED, the diode has a plus and minus the electrode on the both sides. When the electron is from the P to N, what happens is the electron and hole have a recombination, and then when there is some change of the position, the energy from the recombination become the light, and then we can control the emission light from the violet, the UV from the red IR. And then what scientists found is that there are some key material to define the wavelengths for the violet LED, UV LED is the content of aluminum and gallium and indium inside. Actually, for the UV LED, there are not much about the indium, and especially for the UVC, there is no indium. So only aluminum and gallium is there to make the UV LED. So for the UV light, the junction LED, so the junction layer, we say that the active layer to make the light is a aluminum gallium nitride material like this. So in this case, the nitrogen is here, and then the composition of the aluminum and gallium makes the here, then the wavelengths become very short, like close to the 200. And if gallium is high, then it becomes close to the blue. So actually, if there is a pure gallium nitride layer, then the light maybe is close to UVA wavelengths, and then the wavelengths of the blue. You know that to make the white, usually we use the blue LED together with the yellow phosphor. In case the emission layer in LED is the indium gallium nitride, so there is some indium content there to go to some longer wavelengths. So see that the aluminum and gallium and indium is the composition is very important. And then another thing that you must understand is that actually the UV ultraviolet means that it's very high energy, and then when there is the hole and the electron recombinate, there should be direct recombination. It means that between there there is no other energy layer. So that's the difficulties to make the UV LED, and that's the reason that even the blue is 20 years ago, but the UV is still the efficiency is very, very low. So how much different? So for you know that actually for the LEDs, the most efficient LED currently in technology is the UVA material. So like the 395 wavelengths, the efficiency is much higher than the other wavelengths. It's even better than the white LED. So in case the work program efficiency is for the 395 is more than 60%. And then when it lower like the 365, it become like the 40 to 50. And then it's under the like 300 nanometer over the 260. and it become the like lower than 3 actually. So currently the efficiency of the LED is very low. However, in the future, I think it become more than 10, 20, then it can exchange all the mercury lamp into the LEDs. So if you are considering using the LEDs, then I think that it's a good time to try. And then you will see that how it improve and then together with your technology. So as I said, that the aluminum is the very important role to make the UV LED. And then current like the current our UVC 275, the aluminum content is more than 50%, and then gallium is another 50. So in here you can see it's the SIMS data, and then you can see the content of the aluminum and gallium composition. So to make the LED quantum well, there is some there is some ratio difference of the material, and then there is a deep wear, and then the barrier, so that the for the 275, about the 50% is the aluminum, and then the other is the nitrogen. So like UVC is almost 50%, and then for the UVA 365, the aluminum content is less than 5%. And there is some difficulties to make the LED while we are using the aluminum content. You know that when we grow the LED on the substrate is the sapphire substrate. It means it's different material. I think some of you knew that how it's difficult to grow some crystal layer onto some different material. And then currently the dislocation density of the UV LED is the 10 to the 9 defects there. So like the 10% of area has some defect there. So the scientists and engineers are doing to how can I say that recover that defected area. So for the blue LED, it takes more than 10-15 years to recover the whole. But I think our engineer has already has some experience, so that it may not take like 10 years. I think it will take less than 5 years to get the lamp efficiency. So currently, what we need is the high quality epi layers. We need to have the very high quality aluminum gallium nitride layer, and then for that the good quality aluminum buffer layer, and then some n-time layer, P layer is required. And another difficulty of the UVC LED is that the P ohming layer. So you know when the light is generated in the active layer, the light have to be through the whole layer and then to outside, right? But it means that the other layer, P layer or N layer, should be transparent to the emission layer. So it means that they have to have a much higher band gap than the active layer. So even the current quantum error is difficult, and then we have to have a more difficult step to make the P-type layer. And then many companies has not succeeded to get it. So the transparency of the P layer is very low, and then so that's the one reason that the efficiency is not very high. So another hurdle is how to make the P argon ohmic control layer. And then so because of this the transparency problem, every UVC product, the LED is the flip structure. So it means that the light is not from the top layer, it's from the backside, the sapphire layer. And then there have to be flip structure is required. And then from all these, the workflow efficiency is very low, like about 3%. So that's the one hurdle that the efficiency is low. But as I said, we already have some experience in the LEDs, and then that will be overcome very well. And then Seoul Biosys has developed the UV LED more than 20 years, and then the second generation technology will help to be improved this UV technology also. So the Seoul Biosys is not the first company to make the white LED, but for the UVC technology, I'm sure that the Seoul Biosys is the pioneer of this one since early 2000. So below this one is the TEM image of the each layer. So we could see that some aluminum and gallium nitride is agglomerated. So I make some simple schematic layer, which I explained in bubbly. So this is the general blue LED. So from the bottom, this is the sapphire layer, sapphire substrate. It's very crystallized and then it's very transparent. We grow the gallium nitride crystal structure on the sapphire substrate. But even though that we have some technology, still there are some disinfect. So to reduce the disinfect, we grow high, like so actually we only need the active layer, but to support that and then to have high quality active layer, we grow like several micrometers gallium nitride layer. And then another role of the gallium nitride layer below here is to transport electron to the active layer. So electrode here, and then the electron move to this active layer to the N layer. So the LED has the electrode layer, the area is very small because the other area is for the light extraction. And then for the flip chip, the light can be through the bottom without any the blocking layer, so that we use the flip chip for the UVC. So this one is the active layer, which I mentioned before, like the light emitting area. So this is also the PN junction of the LED. So every light is generated from the active layer, and then the efficiency of the extraction is to depend on how we can extract the light from here to outside. For the blue LED, the gallium nitride, the reflective index is about 2.4. And as you know, the air is 1. So it means that if the light goes through the air, there is the total reflection angle. So not every light generated can be through it. Some of them is just reflected back. And then when it's reflected back to the active layer, then some light can be absorbed by it because that the band gap is the same as the generated, so it can absorb like the solar cell. So there is some loss. So it's important to have how can we extract light from the generated one. So to solve that one, so actually we invented the vertical LED structure. So here you can see some triangle shape on top is roughened the surface, right? This is to improve the extraction efficiency from the inside to the outside. So UVA LED, the vertical structure is used. So every Seoul Biosys, the violet technology used this roughened surface for the UVA wavelengths. So that the light is generated can be through to the outside using this the roughened cone, so that the total reflection is reduced much, and then so the structure, the efficiency is very high. I think that's the one reason that our UVA 395 wavelength is much efficient than the blue or white LED, because that we have a special structure for it. And then some high power LED for the general lighting has some similar structures. So for the UVA vertical structure, the pad is actually on the bottom side together. So compared to the blue LED, some lateral one, the sapphire is the insulator. So there is no the resistance is too high, so the electricity cannot be supplied. But however, in case of the vertical LED, the sapphire is removed. Instead of the sapphire is removed, and we put the metal substrate there, so that you can have the M pad on top and then the P electrode on bottom, so that the efficient the thermal dissipation and the other things can be much more efficient than the blue LED. So like here, so active ray is here, and then when light is generated, the first one is it can be through the surface very well because the surface is very roughened. So there is no total reflection effect. And another thing is that on bottom side there is the reflector matter is disposed, so that the light from bottom can be reflected back to the top, so it can have another extraction. So compared to the blue LED, UVA is much efficient than the blue, and then it's more expensive process. And then for the UVB and UVC, it's the flip chip technology. And then why we cannot use the vertical, right? So somebody asked me why UVB and UVC cannot use the vertical structure. And actually, 2 years ago, LG Innotek has developed some process to make the vertical LED with the UVC, but you may know that they failed and they closed the business because of the failure. So there is the difficulty of using the vertical structure to the the flip chip technology, the UVC technology, because one reason is to remove the sapphire substrate from the blue to the vertical structure. The difficulty, the way to remove the sapphire is we call the LLO, is the laser lift-off technology. The way is that the laser through from the outside to the bottom, the boundary of between sapphire and gallium nitride, the laser is observed by the surface of the gallium nitride layer. And then actually the gallium nitride band gap is much lower than the laser, so they can be observed well, and then we can easily remove the substrate. But for the UVB and UVC, you may remember that I said that the band gap is very high. So most of the energy from the laser cannot be absorbed by some boundary layer. So it affects the active layer, like here. So it damages the epi layer. So the reliability is very low. So at the first time we saw the LG Innotek vertical LED, many was very surprised, and then was very happy to have a high efficient. But soon they noticed that the reliability is very bad. Like the lifetime is less than 1,000 hours. So we cannot use most of the applications. It's only for just for good looking, right? So white cap, the UVC is the current technology is the flip chip is the necessary for that. So this is the real image of the UVA vertical and then the UVC, the flip chip. So from now on, I will call the flip chip LED as a white cap, and then I will show that the next page what is the difference between the flip chip and white cap. So anyway, so now I will explain more. So this is the real image of the product, and this is the right one is the N electrode, and from here too. And this is the P electrode because it's the flip chip is the two pad on one side, so we can see. The reason that it's bright, and this is gold. gold surface, and then from there is a very thin line. It's the extension of the electrode, because this area is the lighting surface, and then there is no electrode there. So that to supply the electron to the surface, there is some the extension of it. And then you may have some question, why it's so black? So the previous page, there is the roughened surface, right? And then the roughened surface is good for the light extraction from the inside to the outside. So when it's looks black, it means that actually all the light to the surface is just through inside. So no light come back from there. So there is black. So this is very roughened surface, and every light goes through the inside directly. So there is no reflection. So we make the very good surface of the roughened surface. And then compared to here, the flip chip, the sapphire is very transparent, right? So even though this is through the sapphire layer, sapphire is very transparent, so that you can see some metal layered here. So this is top, this is bottom, and then this is the electrode. And then UV 1400 is the bigger size of the UV LED, UVA product, and then DY4848 is the smaller size of our product. So we have currently we have two versions of the product depending on the operating power and current. So I said that our flip chip, we call it the YCAP. The reason we call it the YCAP is YCAP is a wafer integrated chip on the PCB. So usually, when the LED is developed at the first time, we always need the packaging, and still the very cheap product use the packaging outside, right? And then wire bonding is necessary to have it, because the LED itself has only electrode P and N electrode there, and then we need to connect the N electrode to the packaging, and then P electrode to the packaging, and then it's not very efficient, even though it's very cheap, and the power is low. So currently, after the 2000, we developed the vertical structure, which I introduced the previous page. Currently, the vertical structure is used for the UVA technology. So there is only one bond is necessary. Then the other bond is the P electrode is on bottom side. So you only have one wire bonding is there. And then another is the CSP, the flip chip onto the one sub mount. And then currently most of other UVC producer using the CSP with some the sub mount there. And then to connect the flip chip to the sub mount, they need some special technology, and then they need some the packaging technology is necessary. So that's the one reason that it's expensive to use the package there, because they have to have a special flip chip bonding technology. And then the difference between the CSP, the flip chip, and then YCAP is that we don't need the packaging like the sub mount for the flip chip. What we have is previously you saw that the big bonding pad, right? So the gold area, that's very big. So we can just solder it to the PCB. You don't need the sub mount on there. So we have a YCAP product for the UVC product. So you can save much of process there. So currently, you can choose depend on the choice, like YCAP on board or the packaging. So this is a comparison between the packaging and YCAP. So one big structural difference is the YCAP doesn't have any other sub mount between the PCB. So that's very small. And then we have a very patented technology to have this one, because there is no packages, so we need a special the protection layer there. So another big advantage is that there is no package there, so that the light extraction is much better than package have it. And the other thing is the high radiance power and high current driving is possible also. So you can have some design flexibility because that is
Mr. Wanchun, CEO,
Hello?
I request you to please speed up as it is getting out of the time now.
Oh, okay. So the next one is very simple one. So that is the rear image out to the bond to the PCB, and then this is the rear image of it. And then the last one is that well, I think I already have introduced much of our technology there. Okay, thank you.
Thank you, Mr. Wanchal. Next, our speaker is Mr. A. Madhukar. He is a diploma in MRAC with more than 30 years of experience in service design, project, execution, etc. in the field of heating, ventilating, air conditioning, and refrigeration. Regional Director South 1 for Ishrae Headquarters, Historian Ishrae Bangalore Chapter, Past President of Ishrae Bangalore Chapter, Past President of Ishrae Bangalore Chapter for Society in 2016 and 17. Distinguished Lecturer of Ishrae, member of various technical groups of Ishrae, worked in Mrs. Bharat Electronics from 1991 to 1997 as a technical assistant in plant engineering department with hands-on experience in various types of HVAC system. Currently CEO of Mrs. Climatics, an authorized dealer at Bangalore for Carrier Air Conditioning and Refrigeration Limited, specialized in sales, service, design, project, execution, troubleshooting, etc. in air conditioning and refrigeration. Thank you very much, Mr. Madhukar. Over to you.
Okay, thank you. Good evening to all. My presentation is going to be little bit opposite to, hope I am audible. Can you all hear me?
You are.
Yeah, okay. So my presentation is going to be something different. The other two speakers who spoke ahead of me spoke about the cleanliness that can be encountered, but I am getting into something that what is more important when it comes to saving energy, that is lighting, which is very important when we design a HVAC system. So with, I would like to start my presentation with that. So my this thing would be just a disclaimer which says that these are certain views of the speaker based on the experience, and probably none of us endorse this as the right way. But at the end of the day, there are some references which are also being made, like our Ishrae 90.1, 62.1, Ishrae weather book and things like that. So I have made some references for the figures for this presentation, and I would like to move on with the presentation. And if you have any questions, you can just put it in the chat box, or we can unmute yourself and then we can speak later also. So now, what is air conditioning? Let's first understand the basic lines of air conditioning. We all know that it is just maintaining temperature or humidity, but it is not only that. It's a process where we maintain temperature, humidity, movement of air, cleanliness and odor. And most important, all this has to be simultaneously controlled in an enclosed space. Unless the space is not enclosed, none of these can be controlled. And unless you control all this together, then you are not doing air conditioning. So this is as far as air conditioning is concerned. Then the next thing is, what ton of refrigeration? I mean, all of us are aware that we need 1 ton of air conditioning system, or we need 100 tons of air conditioning system, we need 25 tons of air conditioning system. What does it really mean when we say 1 ton or 1 ton air conditioning system? 1 ton air conditioning system means it's the rate of removal of heat. That means if you have a 1 ton air conditioning system, you can remove 12,000 BTU of heat in 1 hour from an enclosed space. I would just like to repeat this. When we say we have a 1 ton air conditioning system, it means that you can remove 12,000 BTU of heat in 1 hour from that enclosed space. Or in other words, if you have a space which has about 12,000 BTU of heat inside that room. And if you have to remove that 12,000 BTU of heat in 1 hour, then you need a 1-ton refrigeration system or a 1-ton air conditioning system. In other words, it's about 3.5 kilowatts or 1.25 HP. Then, so what is heat? We just discussed about heat, that it is a ton of refrigeration is the rate of removal of heat. So what is heat? Heat is a form of energy. It can neither be destroyed nor created, but generally moves from a warmer substance to a colder substance. The unit to measure quantity of heat is the British thermal unit. And we say 1 BTU is the amount of heat required to raise 1 pound of water by 1 degree Fahrenheit. That means if you have 1 pound of water with you, and if you have to increase the temperature of that water by 1 degree Fahrenheit, that means you need to add 1 BTU of heat. Or in other words, if you have to remove 1 BTU of heat, that means if you have to reduce 1 degree of Fahrenheit from 1 BTU of 1 pound of water, then you need to remove 1 BTU of heat. So this is what is the definition of BTU. So then we straight away move to our this thing that we just discussed, that we have to remove heat from an enclosed space. So then what is it that is the heat load, or what is it that is the cooling load? Heat load or the cooling load, the terminology both are the same, even though it is heat and cool. The meaning wise, as far as our language goes, both are same. We call it as either the heat load or the cooling load. Heat load and cooling load is the quantity of heat to be removed from an enclosed space. It includes both sensible heat and latent heat. It is very, very important. That means that there are 2 types of heat, namely sensible heat and latent heat. And we have to remove both sensible heat as well as latent heat from a confined space if we have to achieve air conditioning process or refrigeration process. It is also known as the cooling load, generally expressed in BTU per hour, as explained earlier. Then, so what are the major components which comes into this heat load or cooling load? Let us try to understand. The first one is the heat coming in through the solar. It is very, very important, especially in this platform. As we move on, let us understand. I would like to call this as the light source or the heat source through your solar lighting. Then the next one is the glass conduction, again related to this webinar what we are talking about. Then we have exterior wall. Then we have infiltration. Then we have people, that is called as the occupancy load. Then the most important is again the lighting load, what we would be talking more about in this particular webinar. Then we have equipment load. Then we have the partition walls. We have the floor, that means heat emitted from the floor. And then finally the roof. So these are the various points which we need to consider when we do something known as a heat load or a cooling load. Then, so what are the various types of cooling loads or heat loads? This is known as the room internal load, the occupancy load, the lighting load, the equipment load, the infiltration. Infiltration load is nothing but, for example, you have a window, in between the windows you have some gap, or you have a door. At the top of the door or at the bottom of the door, or even if the door doesn't close completely, there are some small gaps. So whatever air that leaks through that is known as the infiltration load. And then the system gain load, for example, you have a fan motor within the air conditioning system which generates some heat. You have a blower which would generate some heat because of friction. Then you have air which is passing through the ducts which can also generate some heat. These are known as the system gain heats. And then the miscellaneous sources, then the outdoor load, that is your ambient conditions, and then the fresh air or the outside air, which we generally consider when we take up the heat load calculation. Then coming to the internal loads, we talk about internal loads, external load, and other loads. Heat gain by conduction through walls, roof, windows, then solar heat gain, which we'll be discussing more as we move forward. Then internal load, that is the lighting. We will be talking more about that as we move on further. Then, why is it important that we need to collect the orientation of the building? That is the latitude or the longitude of the building, because the sun, the heat that comes through because of the radiation of sun or the heat through the sun plays a very, very important role. For example, if you have a glass on the west side, let us say, for example, you have a huge French window for the light, which you would like to have to bring in a lot of light during the daytime. You have a huge French window either on the east or west. Now that would bring in a lot of heat through your solar heat gain. So it is very important for us. I'm not telling you it is not right to have. If it is always, you can have whatever you want to have, but we need to consider this aspect when we do something called as a heat load, and this plays a very, very important role. Then the dimensions of the building, height up to the ceiling, height up to the false ceiling, whether the roof is exposed or covered. Then looking at this, now there are certain things which are very, very important, which are flashing in my presentation when we talk about data. The size and number of windows and the type of glazing. Again, this plays a very, very important role because the type of glazing decides on the amount of heat that is coming in through that, whether it is shaded, whether it is tinted, whether it's a 2-pane glass. I will discuss more about this when we move further during the slides. Then, so the lighting load and the type of light, for example, what type of internal lighting we are going to use, which I'm going to discuss about the various types of lights also, which contribute to our heat load, which I will be discussing about. Now, then the solar heat gain through the glass, again, which is very, very important for us, that is known as the solar heat gain. Then, while calculating the heat, the following conditions plays an important role, like I had discussed earlier: heat gain through conduction, through walls, and solar heat gain through light and the internal load. The ambient temperature also varies in different places. This also again plays an important role. For example, the capacity of the air conditioning system required in Bangalore may not be sufficient with the same capacity of air conditioning system when you go up north, where your ambient temperatures varies up to 50 degrees. Whereas in south, the maximum ambient temperature what you have in Bangalore or Chennai, or to some extent even the metros, is around 35 to 37 degrees. Whereas when you go to remote places, the ambient temperature varies anywhere between 40 to 50 degrees centigrade. So the capacity of the air conditioning system may not be the same. And generally the time considered is 4 p.m. as the peak load for the air conditioning heat load calculation. Now, coming to the heat load calculation per se, we do something called as a heat load estimate, which is captured in the form of a heat load form that is known as the load estimate form. If you look at this, I have highlighted what are all which is pertaining to this particular webinar. That is your load coming in through the glass, that is west glass, east glass, north glass, southeast glass, the skylight, and the type of light, that is in terms of watt per square feet. Please understand, the watt per square feet varies on application to application, which I am going to discuss further moving forward. Now, what is, I had discussed earlier, the orientation of the building. It is important because we need to understand the size and number of windows and the type of glazing what we are going to have. Then, now, how does this matter? The solar factor, that is the K factor or the watt per square meter, what we calculate here, I'm just highlighting here. If you look at the simple table, which I have taken this reference from Ishrae 90.1 for LEED buildings, what it says is, let us take for example, if you have a wall facing north and you have so much, say 126 watts per square meter at 40 degrees north latitude is what the heat that is being emitted through the glass. Now, this is what which I said varies from location to location. As you move from different locations to different locations, this data keeps changing as we move. And all these data are available based for specific city and specific location based on your latitude and longitude in your Ishrae table, that is 62.1 or 90.1. And this table is just a representation from that. Now, how does it impact on heat load or the solar heat gain through glass? Please understand, this can easily increase or decrease about 50% of your air conditioning load. Let me say, for example, if you need a if you have an air conditioning space of 1,500 square feet and you need about 10 tons of air conditioning system to that place, with a normal lighting, the minute you want to bring in sunlight or you increase the glass area, even if you increase the glass area only by about 30%, your air conditioning can increase to as high as 50%, because again, if you have a window on the west, or if you have glass area on the west or the south or the east or the north, during, in our Sanskrit language, we call it as Uttarayan or Dakshinayan, the sun moves from east to west via south in Dakshinayan, and sun moves from east to west through north in Uttarayan. So this plays a very, very important role in defining the solar heat gain through the glass. So how do we reduce the heat through the glass? The options what we have is shading of glass. We can have Venetian blinds or curtains, or we can have multiple panes. This is just a diagrammatic representation here. If you see, you have a shaded glass here. You have sun control films today, which you get from as low as 10% heat rejection up to 90% rejection. You get reflective coated glasses, which disseminate this heat or reflect the heat. It means that it doesn't absorb heat. Or you can also have various types of Venetian blinds or curtains, which you can use to make it look aesthetically nice, as well as it also serves the purpose of reducing the heat that comes through the glass. You can also have multiple panes. Of course, this is quite expensive, but this is the most effective way, because you are creating vacuum in between these two panes. And as long as you create vacuum between these two panes, the heat does not transfer through these panes. So this is how it is beneficial to have multi-pane glass windows, which is the most effective in reducing the heat through the glass. So what are the results? If you look at the results here, if you look at the watt per square meter, what we are considering, if you look at the various types of glasses, what we use, single pane, thickness, interior shading with Venetian blind, if you look at the watt per square meter, it has reduced drastically when you compare it with the previous table of 11.11. And when you compare it with the 11.12, which has got, but however, please note, I have something which is very important here, which I have mentioned. You will have to refer the glass manufacturer's data, where it gives you the correct value of reflective, we call it as the K value. It gives you the correct value of thermal conductivity, which needs to be considered. Then, when you have, say, clear glass, you have coated glass, based on the coating, or whether it is double coating or single coating, two pane or double pane, your K factor varies, or your watt per square meter varies. So this is very, very important for us to understand, that we need to look at the manufacturer's data also, that is the glass manufacturer's data, to get the correct K value or the factor for us to consider. Then the lighting load, you have various types of lighting. So from the sunlight, we move on to the artificial lighting now. We have incandescent bulbs, we have fluorescent lamps, we have compact fluorescent lamps, that is the CFL, then we have the halogen lamps, and we have the light emitting diodes. This is just a picture of an incandescent bulb, fluorescent lamp, then a CFL, then you have these halogen lamps, and then you have these light emitting diodes. So these are the various types of lighting load which we consider when we do the heat load. Now, if you look at the simple formula, heat gain from the lighting, kilowatt says W into FUL or FSA, where W is the total light, that is the wattage that is installed. That means the total light, if you have 10 lights, the total wattage of the lights, then the light use factor, proportion in use, that is whether you are using an incandescent bulb or whether you are using a fluorescent lamp, and then you have the conversion factor, or if you have a ballast, the heat emitted by the ballast also needs to be considered. So this is a simple formula which tells that KW is equal to W into FUL into FSA, which gives you the total kilowatt of the light, that is the heat that is being emitted by the light. Then the light use factor as such as generally it is 1 watt per square feet. along with if you are using special lamps with special ballast, we have a separate formula which needs to be considered. So all these are very, very important when we calculate the heat gain from the lighting source, and all these formulas are available in our Ishrae 90.1 guidelines, or when you say Ishrae, when you look at Ishrae design book of handbook of designs from Ishrae. So generally these handbooks have all these tables which gives you different values for different kind of lighting solution and different kind of heat emitting sources. So the table, like I said, the Ishrae 90.1 gives you the light heat gain per square meter or the lighting power density, so which we need to consider both, and then we have to take it forward when we calculate the heat load for design. So lighting from various sources, let's say for example, you have a hotel, you need to have different lighting for a hotel, you need to have bar and restaurant, you have a different lighting, that is called as a diffused lighting. Then you get into a jewelry store, you have a very bright light. You get into a showroom of textiles, you have very bright light. So each and every kind of application what you have, see for example an auditorium, a convention center, a gymnasium, a motion picture theater, see all these have different values of watt per square meter. I mean, see for example in auditorium you use 6.8 watt per square meter lighting. Say if you look, let us say for example a sports arena, you use 4.7 watt per square meter. So every area has got a defined value, and this is again available in table 11.14 in Ishrae 90.1 standards. Then similarly, if you look at, for example, healthcare facility where you have a treatment room and examination room, you need about 18 watts per square meter. And when you come to a recovery room or when you come to a physical physiotherapy room, you need about say 12.4 watts per square meter. And when you come to, similarly, when you come to various applications, manufacturing facility, when you come to low bay area, high bay area, or different facilities, you need to have different watts per square meter lighting load, which needs to be considered when we consider lighting load for heat load. Then again, what type of light we are going to use, whether it's a fluorescent light, whether it is a luminaire light, whether it is a down compact light, again, or you have non-fluorescent. So various factors are considered with various radiative fraction, which needs to be considered when we take up heat load or the lighting load to be considered. So again, coming back to my last few slides, that is, this is where we capture the data based on the various orientation of the building and the various heat coming in through the glass, and then finally the type of light that is used or the watt per square feet that we need to consider or watt per square meter that we need to consider. With this, I come to the end of my presentation and we are open to questions. I'll stop sharing my screen now. We are open to any kind of questions what we want to have.
Thank you, Mr. Madhukar, for a nice presentation. In fact, this webinar by all the three speakers was very excellently addressed by all the three speakers, which is visible even from the number of questions in the chat box. And there are so many questions that it is very difficult now to cover all the questions. So we'll be taking one question from each speaker, and then remaining questions we can pass on to our speakers, so they will be sending reply through emails. So my first question to Mr. Jiang is, what was the power of the LED and the intensity of UVC at the level of the petri dish? Mr. Jiang, is he there?
Jayhawk,
Jiang, yes, sorry.
I'm here.
the question is for you.
Mm-hmm.
UV LED intensity.
Yes.
UV LED intensity, UVC at the level of petri dish.
Petri dish is so the which means the COVID-19 or some the other bacteria or virus.
Both.
Both.
보스.
Normally the E. coli case we calculated the UVC dose reached 99.9% with the 8 millijoule per square centimeter.
Okay.
And then the COVID case, I cannot answer the dose value because as you know our company policy, the confidential data, so that's why I didn't answer I cannot answer this question. But the bacteria case, the E. coli and Staphylococcus is almost the same dose value, like the 8 to 9 millijoule per square centimeter, and the dose value can calculated some the irradiance value milliwatt per square centimeter times the second, only the time, and we can calculate the dose value. So it means the different LED to the surface distance. So that's why I just explain the equation.
Okay.
Okay.
Thank you.
Thank
And
you.
then we can take another question for Mr. Won Chul Sau.
Yes.
How do you verify the sterilization efficiency on HVAC system with UVC LED module?
So the HVAC module, HVAC unit.
Yeah.
Can you reply again? I didn't. Your
See,
question.
yes, there is a question. How do you verify the sterilization efficiency on HVAC system with UVC LED module?
Yeah. The third party in Korea, they have the 6 cubic meter chamber, and they how to say they input their some the bacteria or virus the particle using the nebulizer, and then they check the initial concentration of the virus or bacteria, and then the HVAC unit or some the air conditioner, they turn on during the 30 minutes. After 30 minutes, they sample, they get some sample in air, and then they calculate some how many bacteria still alive, and then they calculate it.
Okay, thank you, Mr. Wan. So now with this, I think now since there is no time, so thanking all the participants who have put their questions in the chat box. We'll be pass on these to all the speakers, and then they will get answers through email. With this, I hand over to Mr. Ajay of Ishrae for vote of thanks. Mr. Ajay.
Thank you, sir. Thank you very much. I think this is a very good and wonderful start along with a joint program with ISLE and Ishrae. So we had a wonderful participation of 200 plus members. I thank to all the participants who had joined today. Thank you to the wonderful speakers, Mr. Madhukar, Mr. Chechen Cheong, Mr. Won Chul, CEO. I thank you, Mr. Amar Narayan, for starting this. Thank you, Mr. Umesh, Advocacy Chair, Mr. Anand Kumar Naganna, Mr. Deepak, Mr. Krishnachari Ashri, Mr. Chandrabhanu, Mr. Vinod Saladi, who is our program chair for Bangalore, Mr. Ashok, who is the vice chair. I also thanks to Madam Deepa, who is our woman chair national. Thank you, Mr. Prakash Barjatia. Thank you, Mr. Ashi Krishnachar. And thank you, Mr. Girish also, who has very nicely coordinated in this. We will look forward to create many more such programs, and those who want to join Ishrae, This is the society which is giving that knowledge related to all the HVAC world. So can join through our www.ishraehq.in, or you can connect us with the email ID given in the chat box, programs@ishraebangalore.in. Thank you very much once again, and thank you for joining us.
My say will be the final say, sorry to interrupt. And there are a few questions which are unaddressed, and we have made a note of all those questions, and we will somehow reach you and come back with all these answers. We were looking for this program. It has happened successfully. Thank you to everybody once again. Thanks a lot.
Thank you. Thank you very much.
Thanks.
Thank
you.
you.
Thank you.
Thank you.
Thanks for all
Yeah.
your participation.
Thanks.
Thank you.
Thanks, sir. Thank you. Bye-bye.
Thanks. Thanks, Jihad. Thanks.
Thank you very
Wancho.
much.
Thank you. Good day. Bye.
Very nice.
Bye.
Bye.
Thank you. Bye.